Moving right along in our calculus course, we're going to look at some formulas and graphs in this section 1.2. We're going to have several different kinds of functions that we're going to look at, polynomials being one of them. Let's make sure that we understand the terminology and know what a polynomial is. I'm going to be using these terms, and I want to make sure that you and I are on the same page. We may have some idea, but sometimes the little particulars, the little weirdo cases kind of get bound up. So let's look and see what's going on. A polynomial is something that kind of looks like, well, exactly looks like ax squared plus, let's say, 2x plus 1. The degree of this polynomial would be 2. You pick the highest degree that's there. This degree would be a 1, and this term here, this particular polynomial has 3 terms, has an x to the 0 power, and this x to the 0 power would be a 1. So it does have, you could say, technically an x beside it, but that x is to the 0 power. Also, these degrees must be non-negative integers. So this doesn't include something like 2x to the negative 1, where x would be in the denominator, if you'll remember. So that would not be included. If it did have that particular term on it, it wouldn't be considered a polynomial. Rational functions are functions that have a polynomial in the top. We'll call it p of x. So something that looks like the above, where the degrees are all non-negative integers, and I have it doesn't matter how many terms I have. I could have 20 terms there, or 30 terms, or just one term, just as long as it fit the definition of a polynomial over another polynomial, and I'll call that q. These rational functions you kind of have to watch out for, because when you're looking at the domain, I can't have a 0 in the denominator. So let's say that I had some x squared minus 4 over x plus 1. I would have to look at this and note that I can put anything in for x except a 1. So I would have a restriction on a domain. So rational functions have restrictions on domain. So let's restrict domain so that that denominator is not equal to 0. So I'd say x, it can be anything where x is not equal to negative 1. Algebraic functions, we're going to discuss those in a little bit more detail later on in the video. My domain in this particular case is a little iffy, because I can't have negatives underneath my square root if I'm talking about being in on the real axes, or the real coordinate system, because that throws me over into the imaginary. So I want to make sure that I restrict the domain if I have square roots, so that I don't have negatives underneath the square root. We'll look at a few of those. Exponentials and logarithms. Exponentials are where we put x's in the exponent, and logarithms, of course, you'll see the word log or natural log sitting there. Trig functions, sine, cosine, tangent, they're listed. We'll discuss those in detail, I think, in one of the upcoming sections. These transcendentals, if I refer to a transcendental, it could be any of the trig, exponential, log, and then there are more to come. If I talk about an algebraic function, it's some form of a polynomial, whether that be one polynomial over another, so that it would be a rational or just a plain polynomial. Just a special note here, I want to make sure, we have these graphing calculators and we think that they do everything, but I want to make sure that you understand that the graphing calculator is a tool that I want you to be able to use, but don't believe it. This happens to be the graph of y equals the natural log of x, and this is what my calculator is showing me. But that's not really what it looks like. It's just the calculator is graphing this numerically, and the numbers get so small they kind of dead end to the axis. What it really should look like is something that gets closer and closer to that axis but doesn't cross. So if you were to graph y equals the natural log of x, I would expect for you to show me this graph and draw that for me, and not this little pitiful graph, because that right there is bad news. I wanted to show this next example because it's something that you're going to be doing very frequently in your calculus course. The textbook goes over a more simplistic way to solve this because they happen to give you the y-intercept. But if you didn't happen to have the y-intercept, and say you had a point over in this area, you couldn't solve and get the equation of the line using their method. So let's do it in a more general method, because this will work for everything, and this will be the method that you'll use most often anyway. So you would go ahead and get your slope, and you're going to use these two equations. Both of these two equations you should have like burned into your memory by the end of this course. I'll choose, and I can choose either one I want. I'm going to choose this to be 0.1, this to be 0.2. So the difference in the y's, that's going to be 3 minus 6. The difference in the x's, that's going to be 7 minus 0. Slope on this bad boy is going to be m equals negative 3/7. What I'm going to do to find the equation of the line is I've got to plug in a point. And it doesn't matter which point I pick. I can pick either point I like. I pick the coolest point, or the one that I think is the coolest. And I like point number 1 because it does have a 0. So I'm going to do y minus the y value for that point, which is a 6, equals m. I just found that negative 3/7. X minus the x value for that point is a 0. And I will get y minus 6 equals distributing negative 3/7 x, and making it pretty because I like y equals negative 3/7 x plus 6, which is exactly the same thing they got, but a little different method. Next up, I have a cool word problem that has 2 points. $14 gets me 400 CDs sold, and $17 I'll only sell 250. What I'm supposed to do now is come up with the linear equation for demand. So I'll find the slope of these 2 points, and it is, I have to choose one to be 0.1, one to be 0.2, so I'll choose you to be 1, you to be 2. 250 minus 400 over 17 minus 14. Crunching those numbers, I get negative 50 CDs sold per dollar. Alright, so that means for every $1 more that I charge, I lose out on the sale of 50 CDs. Next, I'm going to put this into an equation, and I'll use that same equation that I used above. The y minus y1 equals m times x minus x1. I get to choose a point. I'll just choose 0.1. Y minus 400 equals negative 50 times x minus 14. Crunching those numbers, I'll get that the demand, or y, equals negative 50 times the price, or x, plus 1100. So I have graphed here the model, and it seems to me that if I charge anything much over $20, I'm not going to sell any CDs, is basically what this demand function is telling me. and they want to know how many CDs on average are sold at $20. I would just plug in a 20 for P and crunch my numbers. Oops, I said 1100 and wrote 1000. There we go, that's better. So at 20 I would just plug in a 20 there and I would get, so let's just write this D at 20 is negative 50, oops, negative 50 times 20 plus 1100. I'd only sell 100 of them, that probably wouldn't be very good. Piecewise defined functions are kind of fun. You'll see quite a few of them in the course. Let's make sure that we can do them. They say that I have a piecewise function g, so we'll call it g of x, and it's defined in 3 pieces. Oops, that's not much of a bracket there. Alright, there's my little bracket. I have 2 lines, so 2 linear pieces and just a straight dot. So when x is equal to 2, I'm going to do that one first because it's kind of easy. When x is equal to 2, this function is 3. So I'm going to say it's 3 when x equals 2. Okay, I got that one first. Next, let's look at this line here. This line is valid for x less than 2. And coming up with the equation for this, oh, this one is just a plain old, look, if it's 1, it's 1, if it's 2, it's 2. That's just plain old x. I like that one. Then let's do this third piece here. This is for x greater than 2 because it's valid from here on. Let's see if I can just pick out the slope of this. Let's see, down 1, if it goes down 1, it runs 2. So down 1, run 2, so that's going to be negative 1/2 x. If it were to extend on up, it would hit through 5. So just using the slope-intercept method, I got the equation for this bad boy. Alright, I'm on the interactive book at this point because they just have the coolest thing over here. I can move this slider. I'm looking at an even-powered function, meaning x squared, x to the 4th, x to the 6th, and I can look at what happens as I increase the power. It gets skinnier and skinnier. Beautiful. Let's watch what happens. Same thing happens when I increase the power here. Beautiful. So increasing the power means that it gets bigger faster, would be how I would describe that. Fun stuff. You should move the slider on your interactive book so you can have fun too. Alright, I promised you that we'd look at these root functions, and here we are. As we slide this slider up, let's see what happens as I increase the root. Note that the shape of it is still that same little kind of hook shape, but as I increase the power, it just kind of flattens out. Same thing with increasing the odd root. See how it just kind of flattens out? It still is the same shape, it just flattens out some. Investigate rational functions in depth in this course, but first let's look at them. I'm going to do is hit apps. I'm going to go to number 4, which is polynomial solver. I'm going to pick number 1, which is polynomial root finder. I'm going to choose the order. Now I need to know where the denominator is 0. So that is of order 3. Of course the numerator is 2, but so order is 3. And I'm going to look for the real. I could choose either the decimal or the fractional answer to this. So I'll show you what my calculator looks like. There's what my calculator looks like right now. I'm going to click Next. Then I'm going to plug in my coefficients. For A3, I'm going to have a 1. For the x squared term, I'll have a 2. For the x term, I don't have any, so I'll choose a 0. And then for the A0 or A0 term, I'll choose -6. And then I'll put my screen up. There's what I got. I got 1.34 is about what that x value is. So in listing the domain, if this value right here for x is 1.34, thereabouts, then my domain would be, looks like it can be anything left or right, negative infinity all the way up to 1.34, not include, use a rounding guy bracket, union with 1.34 on up to infinity. There would be my domain. The roots are those places where my graph crosses the x-axis. That's what a root refers to, and it looks like they already have listed this for me. If I wanted to, I could get my calculator to find that root for me as well. Since they have it listed, I'll just go ahead and say x equals 0.85, and if it sometimes it'll cross more than once, and if it crosses more than once, you have to find all those roots. The roots are where the numerator equals 0. So the domain, I'm going to look at the denominator where it equals 0, and the roots, I'm going to look for where, if this equals 0, it's going to be a root. At what point does the function have peaks and valleys? Of course, those are listed, and those are just as we think they would be. How does it behave as x grows large in magnitude? I would say this for this function: as x, and this is my notation as well as why I'm drawing, as x approaches infinity, f of x goes to, looks like it's approaching 3. And what that says is x approaches infinity, the y is getting closer to 3. I need to look at both ends of the function, both the right and the left. So as x approaches negative infinity, f of x is going to, still looks like it's going to 3. Cool. Nice analysis of this rational function. Notice that it is one polynomial over another polynomial following the definition of a polynomial. Your textbook has some lovely interactions. You will want to, I know, go into your ebook and move this little slider so you can look at this for yourself. This first little slider is adding something outside of the function. So this happens to be a cubic, and this d is just being added on the outside, and if I increase that d, what happens is it shifts vertically up or down. Negative, it shifts down. Positive, it shifts up. So this is called adding on the outside. I'm going to be talking about inside and outside functions quite a bit. So try to notice if something is on the inside of the function or the outside of the function. So adding on the outside is a vertical shift up or down. Oh, that's what it says right there. Notice that this is something on the inside of being added. And they did a subtraction, which is kind of a little weird, but notice that this left-right shift is backwards, because if b is positive, meaning x minus some number, it moves to the right. If it's negative, what you have is x minus a negative value, which negative makes it a positive, so it moves to the left. So horizontal shifting to me is always backwards, because positive means that you'll move the other way than I thought because of the fact that this is a subtraction. All right. Looking at this next, I am multiplying on the outside. Multiplying on the outside as that value gets bigger. Notice this gets taller. It happened the same way with our roots, didn't it? And as it becomes a fraction, it gets really wide. And if it's 0, of course, it's flat. All right. Next, what we do is we're looking at a C, but this C is negative. Same sort of thing. And we say that it is reflected about the X, isn't it? So that negative does a reflection. Let's look at what goes on here. And all this is doing is it's making it so that I can look at where numbers are in a function and know how it has affected the graph and kind of get some idea of how it's graphed. So let's look at an A on the inside. An A on the inside, if it is a larger number, it gets really skinny, and then if it is smaller number, it widens out. Now they've done this with a reflection, so let's look at it with the reflection as the value gets larger, and watch it get steeper and more shallow. And this is our horizontal scaling. Alright, this next one is really cool. As I am looking at this parabola, let me explain what we've got going on here. The A is a multiplier on the inside, C is a multiplier on the outside. So let's see. D would be my vertical shift up and down. B, because it's added on the inside, would be that horizontal shift. C would be that vertical stretching or shrinking, and the A would be the horizontal stretching and shrinking. So let's see what's going on. Here's just a regular parabola, and what we've done is we've shifted this parabola. Looks to me like it has exactly the same shape and everything, and I think the only thing that is moved, it made a horizontal shift to the right. So let's see, that would be the letter B, and I would move that to the right too. And yep, there he sits, and he's right on the money, so I'm pretty happy with him. So that function would then just be written. Alright, let's see if we can get the equation for this. They called theirs F, so I'm going to call mine G. G of X is, it was moved to the right, and that means that B we saw was 2. And that would be on the inside, so inside of wherever there's an X, I write X minus 2. And that is actually my equation. That's all there is to that one. Let's see what's going on with the B guy. Whew, okay, he got wider, so he's got some sort of multiplier on him. He also went down 4. So I'll do the easy part first. So he went down 4. The down is on the outside, that's the D. So I'm going to move this down 4. Oh, well, he didn't get wider at all, did he? He just moved down 4. Cool. That makes it nice. Let me go write that down. Alright, we saw that with this one. It is H, we'll call this one H of X equals, and it's just X squared, and nothing, the B is 0, the C, and nothing that changed there, and it's just the D went down, I think, 4. Bam, there's that one. Cool. Let's go do the last one. Alright, we're going to look at this green guy here, if I can get him. Let's get this green guy. Yikes. I know he's moved down 1. Down is the vertical, so that's a D, so I'm just going to go down 1. Let's see. Looks like that one really has had, oh, you're too much. Okay, perfect. Now, I need to see exactly what kind of shift that it's had. I'm going to choose this C and see if I can make it match up. I did. Oops. Oh, you dog. There he is. Okay, got him. So now what he is C has moved the 0.25 and D is the -1, so I'll go write that down. Alright, so we'll call this next function, we'll call him, oh, how about Z? Z of X equals, and the only thing that changed was the C, which is on the outside, 0.25 X squared, and it went down 1, -1, and there would be that function. And that's graphical transformations. We're on to section 1.3 next. Cool.